Hello everyone. So we are going to continue with number systems. Specifically, we're going to start looking at computer arithmetic. So computer arithmetic. Yeah, however you spell that word, computer arithmetic. And what the first thing we're going to look at is how we represent different numbers in computers, right? So far what we discussed is how to represent whole numbers, so the fives, the fours, and just the positive whole numbers in either binary or hex, right? Either binary or hex, right? So this is all we've discussed so far. But now I want to show you how we can represent negative numbers, right? So the first part is how to present negative numbers. Then after I show you how to do this, we're going to move on how to represent non-whole numbers, so decimal point numbers, the 5.3s, etc., etc. Then we're going to look at representing numbers in scientific notation. Okay, so we have negative numbers. Now, for representing negative numbers, we have three main schemes. These are sign magnitude, we have sign magnitude, we have one's complement, and then we have two's complement, right? Have two's complement there. Okay, so what's sign magnitude? So sign magnitude is basically a way of representing these numbers, right? Representing these numbers. So let's say we have a 4-bit number. Okay, let's say we have 5 bits. I'm going to use 5 bits for this example. Okay, 4 bits is fine. So I'm going to say 0, 0, 1, 5. 0, 0, 1, 0, like that, right? This is 2, right? This is 2. But then how do I get negative 2? Well, what sign magnitude says that this other bit, so remember previously in that conversion box that we had, the conversion box was 1, 2, 4, and then 8, right? But what sign magnitude says that instead of this guy being 8, right, or whatever value is supposed to be, this represents whether it's negative or positive. So in this case, right, in this case, this is 0, negative, so it will be positive, right? So meaning, the way I would get a negative 2 is by saying 1, 0, 1, 0, right? Which will give me, of course, negative 2 there. So this is sign magnitude. And what you notice is that for sign magnitude, our range of values is, we're going to have, of course, this ends up to 7, right? So we're going to have 7 going down to 0. But then there is one funny thing. So we know 0, 0, 0, 0, right? 0, 0, 0, 0. This is 0 for us, right? But one funny thing about sign magnitude is if I make this a 1 and 0, 0, 0, this is negative 0. So it's just one problem with sign magnitude is that you have a positive 0 and a negative 0. So the range moves from 0, 0, this, whatever, whatever. Then from here now we go to negative 0 all the way up to negative 7. So this is sign magnitude, right? So it's just one way of representing numbers. Basically, the leftmost or the most significant bit, if it's a 0, then your number is positive. If it's a 1, your number is negative, right? That's basically what we need to know about sign magnitude. But again, the arithmetic when it comes to working with this becomes a bit complicated because of this one caveat here where we're saying, okay, but we have a negative 0 and a positive 0. Okay. So, moving on from that one, what is the next thing that we have? Well, the next thing that we have is one's complement, right? So I'm going to show you one's complement, then we're going to move on to two's complement. This is one we're going to be working with the most. So one's complement. What one's complement says that, say we have a number 5, right? 5 would be 0, 1, 0, 1, like that, right? So what one's complement says that you invert all these different bits, right? So in order to get a negative 5, what we do is that we invert the bits, meaning the zeros becomes 1s, or the zeros become 1s and the 1s become zeros. So it would be, this 0 would become a 1, this one would become a 0, 1, 0. So this in one's complement, right? In one's complement representation of negative numbers, this is negative 5, right? If it's just normal representation, this would be 10, but in one's complement, this is negative 5. But again, one's complement also suffers from the same problem that we had with sign magnitude, in the fact that we have two zeros, right? So 0 would be 0, 0, 0, 0. But then what I can then do is that I can say negative 0 is 1, 1, 1, 1, right? So this is a problem, right? So now, what? So this is just one's complement. Just make sure that you just invert the bits and boom. And even the arithmetic for these guys becomes very funny. So quite right, I can get, okay, 0, 1. If I add these together, this would give me 1, 1, 1, 1, which would be negative 0, right? But then let me try getting something like, let me say I have 5 there, right? So I have 0, 1, 0, 1. Then there now, let me say negative 2. So 2 is 0, 0, 1, 0. So negative 2 would be 1, 1, 0, 1. So this is just negative 2. So what I'm trying to demonstrate is actually right. But then I'll get 1, 1, 0, 1. Let me try adding these two. So the way we do arithmetic, and I'm going to show you this a bit later, but the way we do arithmetic is I have to say 1 plus 1. This is what? This is 2, right? And what's 2 in binary? 2 is 0, 1. So I'm going to say 0, carry the 1 there, right? 0, carry the 1. Which you then have, okay, 1 plus 0 plus 0, which is just 1 itself. 1 plus 1 is 2. 2 in binary is 1, 0. So this would give us 0, carry 1. 1 plus 0 plus 1, this is 0, carry 1. Which is funny. I did 5 minus 2, but this gives me what? So we ignore this bit first of all. We're working with 4 bits. So any bit that exceeds that, we call it an overflow, and we just ignore it. So we have 4 bits here. Now these 4 bits, this is 2. But we know the answer is supposed to be 3. Why? Because of that it's extra 0 there. Of course, all these fancy things that happen with this one. So now, 1's complement has this issue, right? 1's complement has this issue. And what you know is that if we try to do more arithmetic here, right? If we try to do more arithmetic, so say for instance, I come and say, say for instance, I say, okay, I still keep my 5, and then negative 3 would be 1, 1, 0, 0, right? This would be negative, this is negative 3. Let's try adding this. 0, 1, 0, 1, 0, 1. So 5 and negative 3, right? So that would be 1. That would be 0. That would be 0, carry 1. That would be 0, carry 1. Again, funny thing is, my answer here is supposed to be 2. But I get what? I get a 1. So what you know is that they'll always be off by 1. So this is why we have what we call 2's complement. And basically what 2's complement says is that just add a 1 to your 1's complement. As in, that's one way of converting 2's complement, right? So we're going to have 2's complement. 2's complement. Basically, what 2's complement is that, say I have my 5 here, right? I have my 5. This 5, I first of all, this is 5 in binary, 0, 1, like that. I then, to convert this to 2's complement, which is a better way, and the mathematics actually checks out in 2's complement, as I'll demonstrate. But basically, what we have here is, I first of all convert this to 1's complement, which is by inverting the bits. So it should be 1, 0, 1, 0, right? I just invert the bits. Okay. Then now, from this point onwards, what to do now to convert this? So this is negative 5, right? To convert this now, to get negative 5, I then just add 1 bit there. So this would then give me 1, 1, 0, 1. This is negative 5 in 2's complement. So this is 1's, this is 2's complement, right? So this is 1's complement, this is 2's complement, right? So this one over here, now what makes this one better than the 1's complement? Well, for this one, the mathematics checks out. Remember, the problem we're having here is that no matter what we do, if it's in 1's complement, the difference was always at 1 there, right? If I was to get 9 minus 10, I would get, if I was to get 9 minus 10, I would of course always have that issue there. But with 2's complement, we basically get rid of all of that, right? With 2's complement, 1, we don't have 2 zeros, so we don't have a 0 and a negative 0. We just have a single 0, right? Secondly, our mathematics checks out, right? So To convert to two's complement, you can use this quite right. But personally, what I like doing is, remember that gadget box that we had there, right? That box, so I said 8, 4, 2, 1. This is for 4 bits. Remember, for 5 bits, it would be 16, 32, etc., etc. But one thing that I just like doing is the leftmost bit, this one, right? Just put a negative there. So no matter what value is here at the most significant bit, the leftmost bit, just make this negative. So for instance, if I had 16, 8, 4, 2, 1, this would be negative 16. If I started at 128, blah, 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 going up to 1, this would be negative 128. So for this one, always just make sure that your leftmost bit is what? Is negated, right? And then we can simply just do the math. So I can say, how do I get negative 5? I'd say, first of all, since it's negative, I know it lies within the domain of negative. So I'll put a 1 there, right? So I have negative 8. What do I have to add to 8 to give me negative 5? I need to add a 3. So a 1 there, right? 0. This is 3, negative 8. So negative 8 plus 2 plus 1, which is negative 5. So personally, I just like going for this rather than getting the ones complement of the number, then adding 1 to it. I like doing this one for really quick. Yeah, so you can use this one. I'm pretty sure you can use both of them. Yeah, you have to ask your lecturer which one they prefer, but yeah, I'm pretty sure both of them are applicable in this case. So you can either do this, you get your number. So if we've told you to say, okay, okay, just some quick work, just some quick work. So first of all, conversion. So basically, we just want to convert the following numbers, right? So convert the following. So let me even just type this out. So basically, what we want to do is what to say. Convert the. We're gonna say represent the following numbers in one's complement, so in signed magnitude, one's complement, and two's complement, right? Just for practice sake. And then you can also just try these out. So I'm just going to pick up some random numbers, and then I'm just going to then go on and convert those. So we're going to start off with 15, right? I'm going to start off with 15. And then over here, I'm then of course going to explain certain concepts. So 15, negative 22 there. So 15, negative 22, negative 50, negative 8, right? So each of these we're going to, of course, have to represent them in that case. So first of all, we're going to start off with 15 there, right? So I'm going to start off with 15. Simple one, right? What is 15? 15, of course, in sign magnitude, the first bit is going to have to be a 0, right? So it's positive. Then what is 15? 15 is 4 ones, because we're going to have 8 plus 4 plus 2 plus 1, right? 8 plus 4 plus 2 plus 1, this is 15, right? So this is in sign magnitude. In signed mag, right? This is in sign magnitude. Right, so this is 1 here, this is 2, this is 4, this is 8, and then this is the negative bit, right? So that gives us what? That one there. In one's complement, what is 15 in one's complement? 15 in one's complement is just 1, 1, 1, 1. No need to even bother ourselves with that. Just 1, 1, 1, 1. Right? Oh, wait. No. Is it? No. My bad there. So, this is one now. I have to talk about the ranges. So, one thing to note about these numbers. First of all, when working in one's complement, or you said, whenever the number at the beginning here is a 0, then your answer is positive. This is one's complement. When your number here at the beginning is 0, your number is positive. If it's 1, it's negative. That's in one's complement. You can always just realize that. Even same thing with two's complement. If you notice, we said we add the 1 here. The moment this is a 1, we know that this is negative. So for all your numbers, the moment you have a 1 in front of here, just know that it's a negative. And then the ranges for each of them. So the ranges for these guys and then I'm just going to generalize them. So let me just create a new page. Okay, so I'm just going to quickly create a new page right in the middle here, so I explain the ranges before I continue. So just going to explain the ranges. So for signed magnitude, right? For signed magnitude, of course, it just depends with how many bits you have. So it's basically, let's say n is the number of bits, right? We say n is our number of bits, right? So for signed magnitude, basically, our range in that case, right? Our range of values is basically going to equal 2 to the power n minus 1 minus 1, right? So this is negative all the way up to the positive there, the power n minus 1 minus 1. And then you can quickly calculate this. So say we have 4 bits, right? We have 4 bits, working with 4 bits. With 4 bits, this would be minus 1 there would be 3 bits, right? So minus 1 there. So this would be 2 to the power 3 minus 1, which is 8 minus 1, which is 7. So in signed magnitude, the biggest numbers we can represent are negative 7, right? Negative 7 and 7, that's the range of values. For 1's complement, right? For 1's complement, what's the biggest number you can represent? Let's say for 4 bits, if n is equal to 4. The biggest number you can represent there is 7. The smallest number you can represent there is a negative 7, right? Is a negative 7 there. Yeah, is a negative 7. So that's the smallest number you can represent. So similarly, this one has a similar range. But then we have 1's complement, right? We have our 2's complement. Now, when it comes to 2's complement, our range is rather similar. But what we're going to have is the negative number there, right? We're going to have negative 2. Then we're going to have 2 to the power n minus 1 all the way up to 2 to the power n minus 1 minus 1, right? So the only difference is that we'll have more negative numbers. It's more like if you think of 0 as a positive number, in this case, you can basically say we're going to have an equal number of positive numbers and equal number of negative numbers, because in the case where n is 4, we're going to have 0 up to 7, which is 8 numbers. Then we're going to have negative 1 up to negative 8, which is also just 8 numbers. So you can think of it as just being split in the middle there, right? So just one way of thinking of it. So these are just the ranges of values. Now, how does this help us solve this question here, this question for 15? Well, first of all, we won't be able to represent this as just 1, 1, 1, 1 in 1's complement, because this in 1's complement is what? Is negative 0, right? So we're just going to add one extra bit there. This is in 1's complement, right? In 1's and this actually checks out, because if we then come and find the negative of this value, this will give us 1, 0, 0, 0, 0. This should be negative 15, right? Okay. Then now in 2's complement, right? How do we do this in 2's complement? So for 2's complement, we're then just going to, in 2's complement again, we just keep it like this. Remember, this is a positive value. We haven't complemented it anyway. So it's just going to be 0, 1, 1, 1, 1. So for the most part, positive numbers stay the same. Whichever way we're representing them, positive numbers stay the same. Now let's look at the negative numbers, which are a bit more interesting. Okay, so negative 22, how to represent this one, right? So in signed magnitude, right? In signed magnitude. So first thing we're going to do is that we're going to first of all find, so it's in signed magnitude, right? So in signed magnitude. So we're going to find what is this one, right? So my approach for doing this is, what's the closest power of 2 that we can find, right? What's the closest power of 2 here? The closest power of 2 here that is smaller than it is 16, right? So 16, right? So 16, meaning we're going to need something that has 16 bits. So 16, then we'll have 8, 4, 2, 1, right? And then we're going to need our sign bit there at the end, right? Okay, so what is our number? It's negative, so our sign bit is going to be a 1, right? Then we're going to add 16 to it, right? 16. What is 22 minus 16? 22 minus 16 is 6, right? So 8 can't go into 6, so we're going to say 0 there. 4 can go into 6, we're going to put a 1, right? 6 minus 4 is 2. 2 can go into 2 there, which is a 0, so there's nothing there. So this over here, this first part, this is 22 in binary, right? This is, unless I've gotten my math wrong, but this is 22 in binary. Then since it's negative, we just add an extra bit there to indicate that this is negative in that notation. 1's complement, right? 1's complement, okay? So 1's comp, right? What is the 1's complement representation of this number, right? Okay, yeah. What is the 1's complement of this number? Okay, so we're first of all going to convert this to binary as well. We're going to say, okay, 1 0 1 1 0, right? This is our number, right? This is positive 22, right? Positive 22. Remember, I just like adding an extra 0 there, and then meaning we then just invert these bits, right? We then just invert these bits, which is 1 0 1 0 0 1 0 1, right? Which is negative 22, right? Which is our negative 22 there. And then in 2's complement, we can just add a 1, right? We can just go in and add a 1 there, which would be 1 0 1 0 0 1 plus a 1 there, which would then add up to be 0 carry 1 1 0 1 0 1. Then we can use that conversion gadget just to make sure that what we're doing is right. This is 1, this is 2, this is 4, this is 8, this is 16, this is negative 32, right? We can then quickly do the mathematics here. Negative 32, so negative 32 plus 8 plus 2, which is negative 22, right? So that's just a quick way of confirming your answer in 2's complement. So just get whatever you found in 1's complement. Let's make sure that your number in 1's complement, if it ends with a, if you found the positive number here, if the positive of the number ends with a 1, just add an extra 0 there to indicate that, okay, this is a positive number. Just add an extra 0 there. That's why when you invert the bits, it's a bit more obvious, because 1's complement can be a bit confusing at times. But for 2's complement, just get a 1 there, boom, add it. Or you can do that trick of just creating that box over there, and then yeah. Then now, what I can leave for you, you guys can just try solving these questions over here. You can just try solving these two on your own, and then you can send me over your answers and I'll go through them. But yeah, that's basic representation of negative numbers in binary.